In this tutorial we're going to look at covalent bonding, a form of bonding which occurs between generally non-metals and involves the sharing of electrons rather than the transfer of electrons from one atom to another. We'll need to learn that non-metals combine together by sharing electrons, by covalent bonding. We'll have to explain and draw some of these models, particularly for some specific compounds with either single or double covalent bonds, and we'll have to learn a little about the structure and bonding of some of these compounds and how that affects their properties and how these properties are very different from the ionic compounds that we looked at in another tutorial. So we learnt about some covalent bonding in something like C1 when we learnt about the alkanes. We learnt that they had covalent bonds, and at that stage we were fobbed off with the idea that covalent bonds were a shared pair of electrons. Now what we're going to discover is how that occurs. Covalent bonds then occur between metals in the middle of the periodic table largely because they can't form ions, and it takes much less energy to share electrons than to lose or gain large numbers of them. So carbon is a prime example. With 4 electrons in its outer shell, it will share electrons to form a full outer shell rather than losing or gaining 4 electrons. A common compound of carbon and hydrogen is methane. Carbon, with its 4 outer electrons, needs to have 8 electrons in its outer shell. Hydrogen, with 1 electron in its outer shell, would get a full shell with 2. So what happens is that the outer shell of the hydrogen overlaps with the outer shell of the carbon, and the electrons are shared in pairs, as you can see here, so that the carbon gets a share of 8 electrons and the hydrogen gets a share of 2. Each of these covalent bonds, these single bonds here, are composed of 2 shared electrons, or a pair of shared electrons, and we show them in a diagram as these stalks between the different atoms. Chlorine in group 7 has got 7 outer electrons, which means it's got an unstable shell arrangement. So what the chlorine atom does is it shares an electron with another chlorine atom to form a chlorine molecule. We've got a covalent bond between the 2 chlorine atoms, and so we end up with a molecule of chlorine, Cl2. Hydrogen has got 1 electron in its outer shell, and to get a full shell it needs 2. So rather than losing or gaining an electron, it shares an electron with another hydrogen atom to form a covalent bond, a shared pair of electrons, to make a hydrogen molecule, H2. Water, or H2O, is composed of oxygen and hydrogen atoms. Now, although the hydrogen atom could lose its electron and the oxygen could gain an electron to form hydrogen ions and oxide ions, this particular molecule is formed by covalent bonds. So the outside shell of the hydrogen overlaps with the outer shell of the oxygen, and it shares its electrons in 2 covalent bonds like so, and we end up with a molecule of H2O with 2 covalent bonds within it. Carbon dioxide is a little bit more complicated because carbon dioxide has what are called double covalent bonds. Now if a single covalent bond is 1 pair of shared electrons, then a double bond is 2 pairs of shared electrons, or effectively 4 electrons being shared. In order to do this, carbon overlaps its outer shell with oxygen. The oxygen puts 2 into the sharing and the carbon puts 2 into the sharing, and we get 4 shared electrons on each side of the carbon, and we show these bonds as double stalks. So these are double bonds between the carbon and the oxygen. This question is about the structure of the water molecule. We're given the atoms of hydrogen and oxygen and asked to draw a dot and cross diagram to show the bonding in water. So we're going to start off with the oxygen atom, which has got in its outer shell 6 electrons. So let's just draw the inner one there first, although it's not necessary. 1, 2, 3, 4, 5, 6, and that's going to overlap with 2 hydrogens. A hydrogen is going to overlap here, sharing its electron, and another hydrogen is going to overlap here, sharing its electron. It doesn't really matter whether you show these overlapping and the electrons being in between or actually on the lines, but so long as they fall within the overlap, either on the lines or within the lines, then that's absolutely fine. Another example, this one is the atoms in a molecule of chlorine held together by a covalent bond. Draw a dot and cross diagram for chlorine, only the outer electrons, so chlorine's in group 7, so chlorine here has got 1, 2, 3, 4, 5, 6, 7. That's going to overlap with another atom of chlorine, which has itself got 1, 2, 3, 4, 5, 6, 7. So there's a pair of shared electrons there. And for 2 marks, not just the shared pair of electrons, but also the 2 atoms with all their electrons shown. It doesn't particularly matter that you show them some as dots and some as crosses. You can show them all as dots or all as crosses, as I did. Drawing methane, or CH4, drawing a dot and cross diagram for this one. It doesn't say that we only have to show the outer electrons, so I better show all of them. Carbon has got 1, 2, 3, 4, 5, 6 electrons, and that will overlap therefore with 4 hydrogens, one here, one here, one here, and one here, giving a total of 8 electrons around the carbon. Here for carbon dioxide, electrons are shared when covalent bonds are made. Draw a dot and cross diagram to show the molecule of carbon dioxide. This is the harder one. So we start off with a central carbon atom, which has got 1, 2, and then they've kind of helped us by putting these electrons on the outside, 3, 4, 5, 6 electrons, and that's going to overlap with an oxygen. So the oxygen here is going to be, here's my oxygen atom, so there's my oxygen, there's my carbon. My oxygen has got 2 electrons in the center, and then it's got 1, 2, 3, 4, 5, 6, and then my other overlap here, another oxygen, dot in the center, it's got 1, 2, 3, 4, 5, 6, 7, 8 electrons altogether. And I confess that their diagram is considerably better than mine, but you could see that there were 4 shared electrons, or 2 pairs of electrons on each of those double bonds. The next section of work is all about the structure of these covalent molecules. Although there are strong covalent bonds within the molecules, for example here of water, the molecules attract each other by only weak attractions between the molecules. And because there are only weak attractions between the molecules, it does not take much energy to separate one molecule from its neighbours. So these covalent molecules, like water and carbon dioxide, tend to have very low melting and boiling points because it only takes a small amount of energy to overcome the weak attractions between the molecules, what we might call intermolecular forces. So, recapping, there are strong covalent bonds within the molecules, but only weak attractions between them. So when water melts or boils, the H2O molecules are retained as H2O, nothing happens to them, but they separate from each other because the attractions between them are only very weak. Some properties, therefore, of these covalent molecules like water and carbon dioxide. The first we've looked at already. They've got low melting points because they've only got very weak attractions between the molecules, these intermolecular forces, which are easily overcome by a small amount of heat. So they've got low boiling points and low melting points. And secondly, they don't conduct electricity, and that's because they're not made of ions, they've got no charges, and there's no free electrons to carry any charge or electricity through them. So properties of covalent molecules generally, these are molecules like carbon dioxide or methane or water or ammonia or hydrogen gas. They've got low melting and boiling points because of these very weak attractions between the molecules. They don't tend to decompose on heating. So for example, water, when it's boiled, it remains as H2O molecules, even as steam. Those molecules don't break up because of the strong covalent bonds within the molecules. and they don't conduct electricity when they're solid or molten or in solution, because of course there's no ions or free electrons to carry that charge. Finally, exam question: carbon dioxide's got a low melting point. Explain why using ideas about structure and intermolecular forces. Okay, it has strong covalent bonds within its molecules, but only weak intermolecular forces between them, so not much energy is needed to separate them and melt it. So we've said that it's got simple molecules, or it's simple molecular, or it's made of molecules, and it's only got weak intermolecular forces or weak forces between the molecules, explaining the low melting point.